In the preceding part of this tutorial, we looked at objects that were moving in a straight line when subjected to a constant force. In this part of the tutorial, we're going to examine, once again, objects that are subject to a constant force, but without assuming that they necessarily move along a straight line. They might move through two-dimensional space, for example. You've already encountered an example of this in one of your previous practice exercises. Consider the case where you have a particle and it's initially traveling to the right with some horizontal velocity v0, but it's subjected to a downward force F. If you like, you might imagine this is a ball that you've tossed horizontally, and there's a force acting on it, namely the downward force of gravity. How is this ball going to move? Well, as you either know from everyday experience or as you know from working this problem earlier, it's going to follow some curved path. In particular, it will be a parabolic path. But the point is, this is an example of an object subject to a constant force, but it's not moving along a straight line, it's moving through two-dimensional space like this. Now we're going to take up this issue more generally, of two-dimensional motion under a constant force. And let me give you an example which will provide a lot of key insight. Imagine we have a 2-kilogram mass, there it is, and there are two forces that are acting on it simultaneously. There's a 10 Newton rightward force acting on it and a 6 Newton upwards force acting on it. Let's think about how this object is going to move, because in particular, the 10 Newton push to the right is going to cause this object to move along the x-axis. But at the same time, there's this 6 Newton force pushing upwards that's going to cause motion along the y-axis. So this particle here is probably going to move both along the x and the y-axes simultaneously, owing to these two forces. So let's think about how we can analyze this. I want you to imagine that this particle is initially at rest, and then you come along and you apply these two forces. We want to know how its velocity is going to change. It's starting from rest, but as you know, forces change velocities. That's what they do. So how is the velocity of this particle going to change? Well, because it's moving through two-dimensional space, we should break up the velocity vector into x and y components. So we'll write it like this. And the question is, how does the x component of the velocity change? And how does the y component of the velocity change in time? Well, let's begin with the following. Let's think about the horizontal acceleration that this particle is going to experience. Why is it experiencing a horizontal acceleration? Because there's a horizontal force on it, namely a force in the x-hat direction. It's a 10 Newton force acting on a 2-kilogram object, so the acceleration that creates is 5 meters per second squared, the force divided by the mass. If we look in the vertical direction and we want to know the vertical acceleration, well, that's going to be the 6 Newton vertical force divided by the mass. That will give us an acceleration of 3 meters per second squared. Okay, so with that in mind, let's think about how these velocities, the horizontal and vertical components of the velocities, are going to change. So let's fill out this chart here. Initially, we're told that the object's not moving. So let's focus on its horizontal motion first. It's got no horizontal motion initially, but it's experienced a 5 meter per second squared horizontal acceleration. And let's remind ourselves what that means. That means every second that goes by, the object gains 5 meters per second worth of horizontal velocity. So after 1 second, its new horizontal velocity will be 5 meters per second. But then after another second goes by, it gains another 5 meters per second worth of speed, so it's 10 meters per second. And then another second goes by and it's up to 15 meters a second, and then 20. This is what's happening in the horizontal direction. Now let's think about the vertical motion. this object is experiencing a 3 meter per second squared vertical acceleration. What does that mean? It means its vertical velocity is changing by 3 meters per second with every passing second. So initially, the particle has no vertical velocity. It's starting from rest. After 1 second goes by, its vertical velocity will reach 3 meters per second. After another second goes by, it will have gained another 3 meters per second worth of upward velocity, so it's going to be going at 6 meters per second, then 9, then 12, and so on. So both of these things are happening simultaneously. This particle here is simultaneously going faster and faster in the x direction and going faster and faster in the y direction. Both things are happening at once, so its actual motion will be something like this, along some type of diagonal here. But here's the key point. We can write down an expression for the velocity of this object, and we did it by looking at how the horizontal forces affect the motion and how the vertical forces affect the motion. So let's look at this chart here. And if I want to write down a general expression for the velocity vector, both the horizontal and vertical components, we can write that as follows. In the horizontal direction, it's 5 meters per second squared times the time. That's the horizontal component of velocity. And the vertical component of velocity is given by 3 meters per second squared times the time that's elapsed. So let's just check that this works. At time 2 seconds, let's plug that in. If I plug in 2 seconds here, I'll get 10 meters per second in the horizontal direction, and 3 meters per second squared times 2 seconds, 6 meters per second in the vertical direction. So here's the key point. When we have an object that's moving in 2 dimensions, both in the horizontally and in the vertical direction, we can analyze the motion in the xy directions independently of one another by focusing on just the horizontal forces. That determines the horizontal acceleration, and the vertical forces, that determines the vertical acceleration. This is a key idea that you use over and over again in your physics class, and it enables you to break up what would be a more complex problem into 2 simpler problems. Now in this example, I had a particle that was subject to a horizontal force and then a vertical force. But we can turn this around. Let's imagine we have a particle that's subject to a single force. For instance, here's a particle subject to a force F like that. What we can do is we can break up this force vector into a horizontal force and a vertical force, and then we could just do what we did previously. We could focus on the horizontal force, and that will determine the horizontal motion of this particle, and we can focus separately on the vertical force, and that will determine the vertical motion of this particle. In other words, when we write down F equals ma, if we want to, we can break up that equation into 2 separate equations, one in the horizontal direction, one in the vertical direction. So we're saying here that the net horizontal force, or the net force in the x direction on an object, determines the x component of its acceleration, its horizontal acceleration, and the y component of the force on an object determines its y acceleration. And this is wonderful news, because previously when we were considering one-dimensional motion, we used an equation like this, and we studied the motion along the straight line. So that was when it was purely moving along the x direction. Likewise, if it was purely moving along the y direction, we could use this. But now if it's moving both along the x and y direction, we can do exactly what we did before, but separately. One equation describing the x motion, one equation describing the y motion. So in particular, whenever we have a constant force, we can write the velocity of the object as a function of time and the position of the object as a function of time, just like we did before. Namely, the velocity vector at time t is equal to the initial velocity plus the acceleration vector times time. And the position vector is equal to the initial position vector plus the initial velocity vector times time plus 1/2 the acceleration vector times time squared. These are exactly the equations that we had before, but now we see that we can break them up into x and y components if we like. So in particular, let's rewrite these equations in terms of their x and y components. So when we have the acceleration vector, I'm going to write it as it's got a horizontal acceleration and a vertical acceleration, where the horizontal acceleration is determined by the horizontal forces and the vertical acceleration is determined by the vertical forces. Likewise, when we have this velocity vector appearing here, let's write it up. Let's break it up into its horizontal component and its vertical component of velocity. And likewise for the position vector, let's break it up into its x component and its y component. So if I take these vector equations and then express the vectors in terms of their x and y components and separate them out, just look at the x components and then separately look at the y components, these equations become these. And I'd like you to stare at these equations for a moment and focus, for example, on this set of equations. This describes the horizontal velocity and this describes the horizontal position as a function of time. They should look familiar because these are precisely the equations that we used when we were describing one-dimensional motion in the x direction. Likewise, when we were looking at one-dimensional motion, but if it was in the y direction, we would have used these equations. Now what we're saying is if both things are happening simultaneously, namely the object is moving both in the x direction and the y direction under a constant force, then these are the equations that we're going to use. One set for the x direction, one set for the y direction. We'll treat them as independent. Two quick reminders. These equations describing the position and the velocity of an object are only valid if the force on the object is constant. So whatever force is acting on the object, it can't change size and it can't change its direction. If it does, don't use these equations. But if it's a constant force, then these equations are the ones that you'll be able to use to describe the velocity and the position of the object. And secondly, I want to emphasize that in order for you to use these equations effectively, you have to draw a picture and draw your x and y coordinate axes right in the picture. You need those axes to tell, so you're defining what your coordinate system is, and then you can break up all your vectors into their x and y components. We'll see this when we solve a problem. So let's look at our first example. Imagine we have a particle. Here it is. It's a 2 kilogram particle. It's in outer space, and we're going to monitor its motion. At time 0, the particle is located right here, namely at the position 2 meters along the x-axis and 3 meters along the y-axis. So its initial position vector is this, 2 meters in the x, 3 meters in the y direction. The particle is initially moving at 3 meters per second in this direction, namely at 30 degrees below the horizontal. So it's initially moving along this line here, that's its initial velocity. But there's an upwards force of 10 newtons, constant steady force of 10 newtons acting on this particle. And we're interested in describing the behavior of this particle. In particular, we want to sketch the particle's path. We want to construct the equations describing its position and velocity as it moves. And then we want to answer some specific questions. The first question is, at time t equals 2 seconds, where's the particle going to be? What is its velocity and what is its speed? Next, we might want to know, what is the particle's x position when its vertical height reaches 4 meters? And the third thing we might want to know is, what is the lowest point on this particle's trajectory. So let's start by thinking about how this particle is going to move and trying to visualize its motion. So here's the particle, and its initial velocity is in this direction. In other words, its initial velocity has a horizontal component. It's moving somewhat to the right, but it's also moving somewhat downwards initially. Now, this particle is subject to a 10 Newton upward force. So let's think about it. There is no horizontal force acting on the object. There's only a vertical force. So if there's no horizontal force, then the horizontal motion of the object won't be affected. So however fast it's moving horizontally at the beginning, it's going to continue to move horizontally at that same rate. But now let's look at the vertical motion. Initially it's moving downwards vertically, but there's an upwards force on it. So in the vertical direction, what's going to happen is that since the force is opposite to the initial direction it's moving vertically, if we just focus on the vertical motion, what's going to happen is that the particle is going to start moving downwards. It's going to slow down, stop, and then it's going to start moving upwards faster and faster and faster, owing to this vertical force. So, roughly speaking, the particle will look, its motion will look something as follows. In other words, it will start going down, but slowing down, slowing down. Its vertical motion will stop, and then it will start going upwards vertically. And all that while, as it was going along like this, it was always moving horizontally because the horizontal motion wasn't affected. Okay, well now let's see if we can be a little bit more precise about this. Let's start by identifying some things that we know. The initial position of the particle at time 0, we're told in the problem that it's 2 meters in the x direction and 3 meters in the y direction. That's its starting position. We can write down what its initial velocity is. So the initial velocity vector is 3 meters per second in that direction. So let's break up this initial velocity into its horizontal and vertical components. That's what these red arrows are. From trigonometry, we see that the length of this red arrow here is going to be 3 meters per second times cosine of 30. And so that's the x component. If we look at the y component of the vertical velocity, that's this one here, that's going to be, the size of it is 3 meters per second times sine of 30 degrees. But notice that this arrow is pointing down, which is in the negative y-hat direction. So its y component of velocity at the beginning is minus 3 meters per second sine of 30 degrees. If we plug in numerical values for cosine of 30 and sine of 30, this just becomes the following. The initial velocity of the particle is moving 2.6 meters per second to the right and simultaneously moving 1.5 meters per second downwards. That's what this vector is right there. The idea is we want to break up all the vectors into their x and y components. Likewise, let's look at the acceleration vector. There's no horizontal forces pushing on this object, so there's no horizontal component of the acceleration. However, there is a vertical force on the object, 10 newtons, and this mass is 2 kilograms. So therefore, the vertical acceleration will be 5 meters per second squared. And that will be in the positive y-hat direction. Because remember, the direction of the acceleration is always in the direction of the force. Okay, so here we have the initial position, the initial velocity, and the acceleration all broken up into their x and y components. Now, we've just seen that the general equations for constant acceleration can be written as follows. The position as a function of time is given by this in the x-hat direction and by this in the y-hat direction. Likewise, if we focus on the velocity vector, it's this in the x direction and this in the y direction. So we've drawn a picture with a coordinate system explicitly drawn out. We've visualized the motion. We've broken up all the vectors that we know of into their x and y components. We've written down the general equations of motion for a constant force problem. And now what we're going to do is plug in what we know. Namely, if we know the acceleration, we're going to plug that in. If we know the initial position, which we do, we're going to plug that in. And if we know the initial velocity, which we do, we're going to plug those in. So I'm going to take what I know here and substitute in those terms. And if I do that, you end up with this. Okay, you can check that for yourself. It's just straightforwardly plugging in from here, substituting in. These equations now describe the position vector and the velocity vector in terms of their x and y components. And that's going to be very useful to have broken up the vector into horizontal and vertical components here. In particular, these equations are going to tell us everything we want to know. This tells us where the particle is at any time. Plug in your favorite time, you'll know where the particle is. This equation tells us its velocity at any time. Plug in your favorite time, you'll know what its velocity is at that time. So now we're in a position to actually address the questions that we were asked in this problem. The first question that we were asked is, at time t equals 2 seconds, where is the particle? What is its velocity? And what is its speed? Well, on the preceding slide, we have an expression telling us the particle's position as a function of time. So if we just plug in t equals 2 seconds into the position expression that we have, we end up with the following. And you can check this yourself numerically. You'll get 7.2 meters in the x-hat direction plus 10 meters in the y-hat direction. This is where the particle is. Here it's x and y coordinates at time t equals 2 seconds. On the preceding slide, we had an expression that told us the velocity of the particle at any time. So we plug in t equals 2 seconds, and this is what we get. The velocity vector is 2.6 meters per second in the x direction, and its vertical component of velocity is 8.5 meters per second. We also wanted to know what its speed was, and you may remember that the speed is the size or the length of the velocity vector. And so you get that by using the Pythagorean theorem. Just the way you get the length of any vector, you take the x component squared plus the y component squared, square root of that. That tells you the magnitude of the vector. In this example, it's 8.9 meters per second. The second question that we had was, what is the particle's horizontal position, its x position, when its vertical height is 4 meters? So remember, this particle travels along a path that looks something like this. It's kind of going down and then swings upwards. And we want to know when where it is horizontally when its vertical height reaches the 4 meter mark. Well, that's not a problem, because on the preceding slide we had an expression that told us the position and the horizontal position and the height at any time. So all we're going to do is take the expression for the height, the vertical height, and set it equal to 4, because we want to know what is the particle's horizontal position when its vertical height is 4 meters. So we're going to set its y coordinate here equal to 4 meters. And that's going to occur at some time. It's going to reach the 4 meter mark, 4 meter height at some time. I don't know what that time is, so I labeled the time t sub y equals 4. That's just my peculiar notation to indicate to you that the time that we're solving for isn't any old time. It's the time when the particle reaches the height y equals 4. So here's our basic equation. This is a quadratic equation. It has two solutions, 1.0 seconds and negative 0.4 seconds. This one's, we throw that one out because it's not the physically relevant one, and this is what we want. So we've just discovered that after 1 second, the vertical height of the object is 4 meters. But we weren't asked how long it took it to reach a height of 4 meters. We were asked what is its horizontal position. But that's not a problem because we know that it reaches the vertical height, the specified vertical height, after 1 second. So we'll just plug 1 second into the expression that we have for the horizontal position. So this here is just taking the time that we found, 1 second, and plugging it in to the expression for the horizontal position. And if we do that, we get 4.6 meters. So we've just discovered that after 1 second, it's going to reach a height of 4 meters. And when it's at that 4 meter height, its horizontal position is 4.6 meters over. The third question that we're asked is finding the lowest point on the particle's trajectory. In other words, its smallest y value. So again, I'm going to need you to visualize the motion. Follow the arrow here. The motion looks something like this. The particle initially is going to move somewhat downwards, but then it's going to swing upwards. Okay, and we want to know, as it's going down, what's the bottom of its motion? Where is its lowest point? How low does it get down before it starts swinging upwards again? Now let's think about that for a moment. At its lowest point, so again, you have to visualize it's kind of going like this and then swinging up. At that very bottom of that curve, right at that moment, the particle is moving purely horizontally. As it was going down, let's visualize this again. So we have kind of this U-shaped thing. As it was going down, it had a negative vertical velocity. When it's going up, it has a positive vertical velocity. So right at the minimum there, it has no vertical velocity. It's moving purely horizontally. So it's moving right at the bottom, it's moving horizontally, but it's no vertical motion right at that instant. So what we do is we're going to set the vertical component of velocity to be 0. So this was the expression for the vertical component of velocity. If you compare it back on the preceding slide, this was the expression for the vertical component of velocity, and we're going to set it equal to 0. And if we do that, we can solve for the time when it reaches its low point, and that occurs after 0.3 seconds. So after 0.3 seconds, this particle, which is kind of moving downwards and then starts moving upwards, it reaches its low mark at time t equals 0.3 seconds. And if we want to know where it is at that time, then we go to our good old position equation. Again, turn to the previous slide, and simply plug in the time that we're interested in, t equals 0.3 seconds, and we'll discover that the position is 2.78 meters, that's the x-coordinate of the particle's position at that time, and 2.77 meters, that's its y-coordinate. So this completes our first example. What I would suggest you do is go back and pause the tape and just redo the example. Don't look at how I did it here, but just redo it from scratch. It's good practice for you. Here are some general tips for solving two-dimensional constant force problems like the one we just did. And these tips they might seem all reasonable now, but you won't really understand them fully until you do more problem solving. So at the end of this tutorial, I strongly encourage you to do all the practice exercises that will give you practice using the two-dimensional constant force, dealing with two-dimensional constant force situations. Here are some general rules to guide you through. First, you always want to visualize the motion and draw a very clear picture which always includes an XY coordinate axis. Verify that this is indeed a constant force problem, because before you start writing down formulas for the position or the velocity of a particle, you better verify that the force in the problem is in fact constant, because if it's not, those equations that we've been discussing, they simply do not apply. But let's assume that it is indeed a constant force situation. Your next step is going to be to break up all the vectors into their xy components, because we're going to deal with the x components and the y components separately. Okay. Then write down all the general equations describing the position vector and the velocity vector. If you know the value of the acceleration, maybe you're told it in the problem, plug it in if you know into those equations. If you know the starting position of the object, plug it in. If you know the initial or starting velocity of the object, plug it in. Always refer, in terms of getting the signs correct, plus or minus signs, always refer to your coordinate axes. So when you break a vector up into components, look at the coordinate axes to determine whether those components should be positive or negative. Fifth, if you're given any additional information in the problem, you should use it. And lastly, then try to answer the question that's being asked. And it often helps to refer to your picture, which you've drawn in step 1 here, in thinking about how you're going to answer the question before you actually do. Now we're going to work through another example. Now this example is actually a little bit difficult. We're still going to use the same methodology, but you just have to take care and go through, use that methodology step by step by step. So here's the idea. You take a rock and you throw it from shoulder level as hard as you can. And you watch it as it flies off your hand, and you notice that it lands 30 meters away, and at its peak height, it was about 10 meters off the ground. So that's what you notice. The rock lands 30 meters away, and its peak height was 10 meters. Based on that information, you want to determine what angle did you throw the rock at, and what was the initial speed of the rock when you threw it. Now, even though we're being asked very different questions, we're trying to find an angle and some initial speed, even though the questions that were being asked differed from the questions that we were asked in the first example, the method that we're going to use to solve this problem are precisely the same. And that's the key. You want, in physics, and you'll notice this throughout your physics class, you want to be driven not by what you're being asked to find. If you're being asked to find the angle of something, don't go hunting around for some equation that has an angle in it. Think about the physical situation and what principles you're going to use and the methodology that you're going to use. So let's go through this step by step. We want to start with a picture. So here's a picture. I've drawn a coordinate system. Here's the rock. It's being tossed from shoulder level. That's at a height of 1.5 meters. It's being tossed through the air, goes through the air, and lands on the ground. It lands 30 meters away from where you tossed it. It reaches a peak height of 10 meters. But we don't know how fast it was tossed, and we don't know at what angle it was tossed. And that's what we want to determine. So here was its initial velocity, which I don't know. I do know that whatever the initial velocity is, it has some x component and it has some y component, but I don't know what those are yet. Okay? So this picture encapsulates what I know about the problem. There's one other piece of information. Once the ball or the rock leaves my hand, the only force acting on it is gravity. We're ignoring air resistance. So this rock is in free fall. And we've already seen or learned that when an object is in free fall, gravity exerts a constant downward force on it, and it causes an acceleration, a downwards acceleration of 9.8 meters per second squared. Okay, so here's our drawing. Here's our visualization of the system. First step is, or the next step is, we're going to write down the equations of motion in the horizontal, for the position and the velocity. Here's the horizontal component of the position. Here's the vertical component of the position as a function of time. Here's the horizontal velocity as a function of time. Here's the vertical velocity as a function of time. So here I've just rewritten those general equations that we have. Now, just as another reminder, the only reason I'm writing down these equations is because I verified that this is indeed a constant force problem. There's the constant force of gravity. If it wasn't a constant force problem, these equations are irrelevant. They don't apply. But this is. So we're good to go. So here's the idea. I write down the general constant force equations describing the position and the velocity. Now, I'm going to plug in any information that I have about the acceleration, about the initial position, or about the initial velocity, and I'm going to plug them in. So let's go through this. Here, this represents the horizontal acceleration of the object. But think about it. Once the ball leaves your hand, we just said that the only force acting on it is the downward force of gravity. There's no horizontal force acting on the rock. So the horizontal acceleration is going to be 0. So this first term here becomes 0. I ignore it. The next term is the initial horizontal velocity of the rock when I tossed it. Well, I don't know what that is, so that term, I just bring it down here. And x naught represents the initial horizontal position. So look at my picture here. The rock is starting here. It's starting at the x equals 0 mark. So its initial horizontal position is 0, so that term goes away. So the only term that remains here is this one. Okay. Now let's go over here to this describes the vertical position. The first term here, we have 1/2 a sub y t squared. Well, a sub y is the vertical acceleration. Well, the vertical acceleration has size g, namely 9.8 meters per second squared, and the direction is downwards. So I'm going to replace a sub y by negative g, or negative 9.8 meters per second squared. So this term becomes that. Let me look at this term. It's the initial vertical velocity times time. Well, I don't know what that initial vertical velocity is, so I just leave it alone. This term here represents the initial height, the starting height of the rock. Look at the picture. It's starting from a height 1.5 meters. So I plug in, replace this by 1.5 meters. Then I do the similar thing for the velocity equation. In the horizontal, there's no horizontal acceleration. Ignore that term. And so I just have this horizontal component of velocity. And over here, the vertical acceleration we said is negative g, negative 9.8 meters per second squared. So that's this term. And v0y, I don't know what that is, so I just leave it. So these equations here in red describe the position and the velocity of the object as a function of time. Notice, by the way, that I haven't actually worried about what I'm being asked to find. Remember, I'm being asked to find the angle that this ball is thrown at. In other words, I want to know what is this angle, and I want to know how fast it's thrown initially. I don't worry about that at this point. I draw my picture with a coordinate system. I write down my general equations for constant acceleration. I plug in if I know the acceleration value, I plug it in. If I know the initial velocity value, I plug it in. If I know the initial position value, I plug it in. The method that I'm using is going to be independent of what I'm being asked to find. So here are our basic equations. In fact, what I might suggest you do is pause the video here and write down on a piece of paper these equations so you have them as handy reference. That way you don't have to keep on going back in the video to refer to them. The next step in our problem-solving methodology is to look at any additional information that we're told. And in this problem, we're told that the rock lands, in other words, it hits the ground 30 meters away from where you threw it. So what we're going to do is let T sub L denote the time when the rock lands, and we're just going to go to our position equation and plug in at time T sub L, require that the horizontal position is 30 meters and the vertical height at that time is 0. Again, go back to the original picture to visualize that. But if you plug that in, so we're going to set the x component of the position equal to 30, and we're going to set the height equal to 0. So again, where do these things come from? Just go back to the equations that you on the preceding slide, or the ones that you just wrote down on a piece of paper, and notice that I'm just plugging in 30 for x, 0 for y, and that's occurring at time T sub L, the time when it lands. But we're given another piece of information in this problem. We're told that it reaches its peak height of 10 meters. Okay, so let's think about what this means. And in this case, I really need you to visualize the motion. Visualize this ball or this rock being tossed through the air, and right when it's at the peak of its motion, right at the peak, it's moving purely horizontally. It's not moving up or down. When it's rising, it's moving, it has a upwards motion. When it's sinking, it's got a downwards motion. But right at that turning point, it's neither rising nor sinking. It's right in between, so it's got no vertical velocity. It's only moving horizontally. So therefore, we're told that right at the peak, in other words, when y equals 10 meters, we know that the vertical velocity is 0. That's what the peak means. So we're going to let T sub p denote the time when it reaches the peak. And we're going to go to our equations describing the vertical motion, and we're going to set the height to be 10 meters at the peak. So at the time when it reaches its peak, we set the height to be 10 meters. And at the time when it reaches its peak, we set the vertical velocity to be 0. Again, look at the equations that you wrote down on your piece of paper and compare them to these, and you'll see all we did was say that at time T sub peak, we set the height equal to 10, and we set the vertical component of the velocity to be 0. Okay, and now let's look at what we have. We have 1, 2, 3, 4 equations. Let's count up what we don't know. We don't know v0x, that's 1. We don't know v0y, that's 2. We don't know T sub L, that's the time when the rock lands, that's 3. And we don't know the time when it reaches its peak, that's 4. We have 4 unknowns, but we have 4 equations. So we go ahead and we try to algebraically solve these equations. Now this turns out to be rather messy if you do it by hand. So you might want to use some computer software to do this. For example, Wolfram Alpha you can use and plug this in, it will solve it for you. But when you do that, here's what you'll end up getting. v0x equals 10.92 meters per second. v0y is 12.91 meters a second. The time when it lands is 2.746 seconds. The time when it reaches its peak is 1.317 seconds. Okay, now that we have that, then let's think about what we're being asked to find. The ball was tossed upwards at some initial angle, and we wanted to know that angle. But we've just discovered that the horizontal component of the initial velocity was 10.92 meters per second, and the vertical component of the initial velocity was 12.91. So you draw a little triangle like this. Here's the initial velocity that the rock is tossed up at. And we see then that if we want to find this angle, We know that the tangent of this angle is the rise over the run, 12.91 over 10.92, so we can therefore take the inverse tangent and we could figure out what the angle is. We were also asked to find what the initial velocity was. How fast was this rock tossed at the beginning? Well, we have our triangle here. Here's the horizontal velocity at the beginning. Here's the vertical velocity at the beginning. So we want to know what is the length of this vector. So we use the Pythagorean theorem. This squared plus this squared square root tells us the length of the hypotenuse. And if you do that, you'll get 16.9 meters per second. So what we've discovered is that the ball, or the rock I should say, was initially tossed with a speed of 16.9 meters per second at an angle of 49.8 degrees. So there you have it. Again, I want to emphasize the problem-solving methodology. The idea is you always need to draw a clear picture with a coordinate system. You need to visualize the motion. You need to determine whether this is a constant force problem. If it is, you write down your general equations of motion describing the position and the velocity. You break up all the vectors into their x and y components. You plug in the information that you have, namely if you know the acceleration or the initial velocity or the initial position, you plug them into your position and velocity equations. Then you utilize any additional information that you're told in the problem, and then you attempt to answer the question. Again, you should focus on the practice exercises to get a lot more training with this methodology.